Much about it over a different glass of Pellegrino. Great, thank you. Okay, go ahead.
I have to use the restroom.
Okay, Donna.
Wait a minute.
I'm sorry.
Come back.
Come right back.
I have a question. So, I guess my information is a bit old. I remember electromagnetic fields and waves 1 and 2 with Dr. Bellato in 1987 at Monmouth, and he would say you go back to the simplest element. What is one electron doing? And you describe it. Here's an electron. Imagine it's got mass. Imagine it's got spin. Imagine it's got field. Imagine it's got whatever. This is going through space at some probabilistic prediction. Now you don't know where it is, but you kind of do. And build from there. And his notion was that I have my electron going and defining my current and the voltage and so on. And you mentioned before magnetic current. And I thought I remember a description of I have electric current. I don't have magnetic current. I have magnetic field density. And it's sort of an instantaneous, how do it go? Twisting this way for that field. So if I adjust that field, I adjust this current. If I adjust this current, I adjust that field.
Yes.
So if I do either of those things, they're linked. If I do either of those things, I'm affecting, if one's radiating, I'm affecting that radiation. If I have ground planes, if I have Faraday cages, if I have whatever obstacles impacting either or both of those magnetic and electrical features, then I'm going to dampen it, probably, or siphon it off.
Yes.
And if I'm trying to match it, I'm trying to get maximum power through there, and in whatever form. Why is it that? Sure. Why is it on the edge side, for example? You have the edge strip.
You wanted more? Did you want more as well?
Is it unknown? Like, is it generally like unknown? Like, why it does what it does? I mean, does the corner matter? What are we worried about here?
I don't think I can answer this in very specific detail. But if we get closer to the edge, you have a higher imbalance in the currents.
Okay.
So if you all remember the differential mode versus the common mode.
Yeah.
So the differential mode, which we know it radiates more than the common mode, both radiate, but one is more than the other, or we can say that theoretically one doesn't. But the differential mode will increase if you get closer to the edge. Because theoretically, what we studied is that when we have a big ground plane, we are approaching the theoretical limit of a transmission line behavior, where all the current is balanced and confined underneath. So the differential.
To the extent it comes out, it comes back. It stays there.
Exactly, and confined. Yeah. And confined, because one will say, okay, when I pump 1 amp, I get back 1 amp. But this 1 amp, when it gets to the other end, now we're not talking circuits 1 amp. We're talking J, current density, right? So it's just the 1 amp, it's just the initial thing. And I need 1 amp at the initial thing, that's it. But this 1 amp will spread. You see, then we have J, the current density, and that causes radiation. So in a nutshell, why I like to talk about the microstrip, we're not antenna designers per se, but it really shows the importance of the balance, the critical importance of the balance between the two, of one current versus the other. That's the critical.
I think they're always in balance. It's sort of this inviolate kind of thing. They're going to be. It's going to happen.
That's why some people say no matter what we radiate, no matter what. I radiate not just with joy right now, but I radiate with.
We're happy because we have wireless.
But it's next week. So here, previous. Yeah. So if we look at the transmission line, and this, I'm giving a different perspective here. So this transmission line, the separation between the two lines is very small. So the theory that they taught us in books is based on that. But that theory also says that at the very end, I have an open-ended transmission line. Right. The load is infinite. So now I'm going to talk about the perspective of the load. And I really think what at that time wasn't impressed with practical electromagnetic compatibility engineers who really sensitized me to focus on these aspects. I came back from my high horse, so to speak, to really focus on the physics. And at the end of the day, that's what will prevail. If you see, we expect full reflection, which we call it full maximum impedance mismatch. So there's a full reflection. Next, please. If we separate these, separate them further. Now it's still the same thing, open-ended, but right now I don't have full reflection. Well, we don't have a transmission line concept anymore. We do have transmission line. Maybe there's an application you mentioned earlier, when you were mentioning this interesting problem of transmitting signals over big, I like to use it, big lines.
Yeah.
So they're not electrically, it's not traces with micrometer separation between them, which we use to transmit the 2.45, 5 gig, and 10 and 50 gig. So there's a different, it's not different physics, but it's not the classic transmission line. I like, and if it's interface, does that mean we cannot use it? No, we can, but probably, as you said earlier, rightly, with challenges.
Yeah.
You see, so this I think fits in that perspective, is that we have an open-ended load, but here we cannot talk about wave impedance. The concept of wave impedance is meaningless here. We have to talk about space impedance. Next. So if we look at a waveguide, this is a flanged waveguide, this is a horn, the third tension, and now open-ended waveguide. I want to ask you, which one radiates more?
Depends.
Okay, follow up, because that's a political answer that I've gone way beyond.
So you got the gazettes,
It's
you
really
got
where
the
you're,
But
it's where you're putting that radiated energy.
Wait, how measured?
But
That's the difference, is where you're putting it.
But my question is not that. My question, which one radiates more, irrespective of the direction? Which one?
Well, there's the same
Which
amount,
one
it just depends
radiates
where
the
it goes.
best?
No, I'm not interested where it goes. In other words, 1 watt, 1 watt, 1 watt. Okay.
Yeah. I go
Which
with the
one?
horn.
You go with the horn.
I go with the horn.
Horn. Okay.
I think they're equal, just direct it.
That's what I'm saying.
Yeah.
It's
You know
really
what?
where it's pushing,
It's
it's
the
where it's
arc
pushing the
wave
energy, it's where it's pushing the energy.
You know what? I mean, some of us are biased by previous experience. If I were just coming from my mother womb and you ask me,
Yes.
I would say I really don't know.
Right.
It's as simple as that.
Yeah.
Of course, you're right. It's the horn. That's why we designed horn antenna.
It's what? It's
right?
the horn, yeah.
The horn, because the horn is not just directed, but
It's matching the
reflects.
space better than the other example.
Yeah, I mean, yeah. So, but the
So you should keep your day job.
Okay.
Well, this is why they have that big horn antenna up on the hill.
That's why they- But the question is, how do we understand that? How do we? Next, please.
Yeah, but that's
Well, that's why they have a horn antenna up there.
Next.
Yeah.
So if we look at
I
the
don't agree with that answer.
if we look at the flanged waveguide, and that's a good attitude, by the way, is not to agree. If you don't believe, not to agree.
Yeah.
One should go there.
I understand that ultimately it's more in the direction. It's not more.
It's
Well,
efficient.
I guess, are you saying that
Yeah, it's efficient.
for the waveguide,
Exactly.
the amount of energy radiated, there's additional there's additional energy conducted elsewhere versus radiated elsewhere.
It's overall, if I have 1 watt,
So
I just simplify.
I have a
1
watt going that way.
Most of it will go away, and for the other waveguide, a lot will be back.
By go away, do you mean it is conducted elsewhere, or do you mean it's
Well, no,
radiated
it-
elsewhere?
No, radiated.
Dispersed.
I mean, energy that comes to the end of that waveguide can go one of two places. It can radiate out, which is what you want,
I
Right.
think loss, zero loss.
Or reflect back?
or it can reflect back.
Yeah.
I think like Margaret said,
Okay, I
it's
understand.
just more efficient. It's not that it's putting out more
No,
power
but that's
or more radiation.
but that's the
It's
definition.
just that it's
But that's why we
But there's a
should
different
that's why
impedance
we're
on the
using
free
it.
space side with this, is what I'm
That's the
hearing.
definition of efficiency.
Yes.
That's it. More
Right, but your
power.
That's
question
a very
was
good
which one
question.
radiates
Let's,
more.
can we talk about that
What's
for a
that?
moment?
Say that again.
That there's a definition of efficiency.
Exactly.
That's our
All right,
test.
so we need to
That's our
ask
goal.
you the question
Yeah.
again. What do you mean by your question?
Yeah, yeah.
Okay, so in other words, P out
Yeah.
into the world
Yeah.
divided by P.
So, and
That's it. By the way, I don't like to complicate life.
Good, thank you.
I think it also
But sometimes,
depends-
Life is already complicated, right?
And measuring this thing.
That's why, you know
Right
what?
in front of the horn, it's not
My
really-
wife,
Because you don't have all the requirements in front of you when you're looking at the question.
I guess that makes sense because
And when you explain it to us,
if
that
the horn
helps us
approaches
understand the requirements.
perpendicular, essentially, if the horn approaches the transmission guide itself, it's 100%.
Because some people, like inventors, were used to figuring out what the requirements are without constraint, right? If you're an inventor.
of course. You know
Yeah.
what? I mean, we're engineers. Without constraints, we should not begin without constraints.
Right,
I mean, we know we can solve. Anyone can solve anything. And you know, they say poor money and time.
Isn't it wonderful
Yeah.
mathematicians and physicists can do that?
They can do that,
It's great.
but that's why we make more money than both of them. There's a reason. Really.
Because
There's a
we're trying
reason.
to solve a particular set of requirements.
I had a physics student one time, and it took 1 month to kick him out of my life.
Is the horn at 45 degrees the
He wanted to
appropriate?
come and speculate and theorize and put
not
leg
necessarily.
over the other leg and marvel. We cannot afford it, I said. Sorry.
Once
We
you get
have
to
things
space,
to
you've
do.
got no waveguide.
Yeah.
Waveguide, you got
And miles to
very
go
confined
before we
waveguide.
sleep.
So you kind of find some
The
structures
best
that
of us,
transition
the best of us,
Perpendicular is perfect, that's your actual
ground
waveguide.
their work based on
Flange
substance.
is
That's
tip.
all.
Well,
Yeah.
it's
See, some
So you're
people
trying
can look at this
find-
and
yeah, you're trying to
recognize
find
the
a
horny
structure
antenna, which I recognize the
transitions
horny
between
antenna, but I don't
just
know the
open
answer to the
space and
question.
waveguide.
And then, and because I know why it's
So I guess
there
there's
on
the
the
geometry,
test.
the
You know,
degree,
the guide,
the width of the width of the
20
waveguide
years
itself,
or
the
whatever,
structure of the
40,
waveguide,
30
and
years
then
or
your
something.
explosion.
You might
If
have
we,
to
if we
have
don't,
a
like,
horn
if
that
you look
its
at it, you
taper
implicitly
varies.
know what the
Oh,
requirements
okay, all right,
are.
so it's kind of going,
And some of the
There's all
stones
sorts of
we're not
things you can
experienced.
try.
But you see here, the reason why I'm doing this
not what I
exercise
worry about on a Monday morning.
is to say that
The left-hand example
I really,
is
you
not
know,
going to work.
I know there are horns and they must be designed, they must have been
Too severe transition.
but then I went back and I wanted as an exercise here to see how did we study these.
Yeah.
Next, please. You'll see why I'm looking at this. So, this is to take you into this elegant mathematical principle, Huygens principle, all that business, and I will not spend too much time on this, but these are one more please, and the rest, that's it. I'm not going to spend time on this, but this is a model that will show that we have an equivalent magnetic which is almost twice in magnitude to the electric field at the opening of the flanged waveguide. So there's layer after the layer of approximation. That's the best you could find in textbooks. Now, why should I impress the students of doing this where I can tell them, next please, this is by the way from
the textbook?
Balanis, yeah.
Okay.
Who would go into electromagnetics when
Nobody.
they studied? Nobody,
Not
and
a
rightly
person.
so.
Yes. Nobody.
Right? Because you see, I come from a culture.
Somebody who you'd have to be afraid of has ammunition in the basement. Just saying.
You see, I come from a culture where you really impress people with your analytical knowledge, differential equations, and all of that. And for me, in that culture, we didn't think what's suitable. We didn't think even what we like. Can you believe we didn't think what we from the Middle East? You don't think what you like. You should be good at this. But my point is that this is discouraging. Next, please.
Thank you.
And next.
Next.
Next, please. Okay, no, before. Okay, look at this very simple exercise. Go to HFSS, CST, FECO, whatever, and look at this. Why I'm asking us to do that? Because there's no analytical model. If there's an analytical model, fine, we can theorize. But if you look at the left-hand side, you find that the edges, this is a wave coming,
Yeah.
you find that the edges
Is that an
are...
artifact or is that real edging? You see the
No, just an artifact.
That's an artifact.
Just a
Okay.
boundary, right,
Yeah.
thanks. But it's opening, and the edges, you see, it goes like this, and it flanges.
Yeah.
So there's a sharp transition, okay? So this has a lot of current. A lot of, yes, a lot of current. And then you see the current going further. So what you see on the right-hand side, of course, the middle one is the schematic. The one on the right-hand side is the opening, and you're looking at it from the front, and you're looking at the current on that surface, okay? Wow, there's a lot. There's a lot of edge current. You know, I mean, this gives us a good physical perspective rather than impressing the students with using the equivalence principle. Next, please.
Is there a toolbox in like MATLAB that helps you to do these things?
Unfortunately not, because this is HFSS. It's not hard on HFSS. This shows you the electric field.
Yeah.
But you see the electric field is spreading slowly. Next, please. And this, what is this? This is the electric current, J. This is the magnetic.
So what is influencing that artifact? Is that a temporal thing? Is it the power?
No,
What is it?
you have this discontinuity,
It's just a
a step,
Okay.
and it's the physical phenomenon.
Okay,
I
yeah,
really,
okay.
nothing. I think this is just a null in the field, low value in the field. Next, please. Okay, so this
That's
is
why you got the arc here.
probably yes, because it's a cut.
So
Yeah.
this is the model?
So no, this is looking at the current,
Got
and it's so simple. It's available to many of us. You know what? We can actually first year. I'll tell you at the very end what I did with these models to help students move fast. But my point is that the model could not predict the physics. Very simple and very powerful. Next, please. So this one is a very interesting. This was a paper co-authored by Shin with Lincoln Labs. And the late Professor Khan from MIT, he passed away unexpectedly 15 years ago, I think. So this paper is application of the finite difference banding radiation from heat sink configuration. This was a contract to DEC when I was at DEC. This was a contract, and we used to go and monitor the contract. And I tell you in all honesty, it was not useful. This work was not useful. This paper, are we on record here? It's okay.
I can stop.
This paper actually won a paper.
Delete this.
The IEEE transactions of ENCC, this compatibility award.
Nice.
But the colleagues that were monitoring this work, and I was with at that time, they said this is not useful. Okay? It is a very good, interesting theoretical work. Why? Because the fundamental cause of radiation was not modeled properly in this work. So this type of work, they used a magnetic dipole, just a fictitious thing. Since electromagnetic folks, electromagnetic compatibility are interested in absolute radiation, we're not interested in relative. That's the Air Force, the radar cross-section. In fact, the Air Force never tells you how much power the radar sends. They tell you, can you give me a reduction by 10 dB? Then you go work in the lab and you give them that, but they won't tell you how much energy they're taking because they don't care. You shouldn't care.
Yeah, they're not bounded by the law.
It's absolute. Sorry, it's relative. For us, it's absolute. 20 dB microvolts per meter. That's absolute, right? So you have to meet it. So that's why understanding what makes that chip actually. There's a chip under the heatsink. Chip package, and there's a package under the heatsink. What kind of elementary source that I can use to predict the radiation from this heatsink? Next, please. We'll skip that just to show you some details. Okay, where we go from here? So when the primary current source is known, the culprit is found. As simple as that. I'll go quickly. So that takes you a very quick journey into something I think you'll find it interesting. The mysterious aperture, I call it. Next, please. So apertures show up everywhere, okay? Everything, okay? And the loudest aperture is our mouth. Next, please. So how do apertures radiate? Isn't that an interesting question? Okay? Look at this perspective that I had, okay? I was intrigued by apertures. Before we go any further, if you have a tiny aperture, just a tiny aperture in a metallic screen, do we need apertures? I gave a talk one time and I was really amused by one of the engineers who said, well, you reduce the size. That's one of the reasons you eliminate radiation from an aperture. You shrink the size. It's like telling a chip designer, we have a problem with your 5 gig chip radiation. Can you go back to 200 meg? That's exactly. I mean, apertures, we cannot touch them. If it heats, it doesn't work. We have to have apertures. So the last thing you want to tell the designers, please shrink your aperture. So here's an aperture, and I thought of it that if you have an aperture like this, you have a field coming like this, so the aperture is, let's say, horizontal, and you have a field coming vertical. We know it passes. Why? Because it creates a voltage between the two, so it passes. It's not intuitive, we know. The other field, the horizontal field, we think of it as E0 here, E0 here, in between it has to be zero. That's the typical impression we have, so it doesn't pass. So if we look at the field that passes, if we consider that transmission line, the aperture as a transmission line, what do we mean by that? Not transmission line in the direction of the airflow, but in the other direction. It's a perspective, why not? Based on the physics, that there's a potential difference between the top and the bottom. So if we have that perspective, then right now I can think of, look, I'm imagining, but it's based on the physics. So now I can imagine that E field which is coming, creating a field, a wave that goes both sides.